All right, good afternoon. My name is Riley Edwards and welcome to today's virtual William W. Hay Railroad Engineering Seminar. It's great to see another strong turnout for our seminar, and we have another exciting topic to present to you today. All questions related to either the virtual platform that we're using or today's presentation can be submitted via the questions tab or sent to hayseminar@illinois.edu. The William W. Hay Railroad Engineering Seminar Series is sponsored by the National University Rail Center here at the University of Illinois. On behalf of all of us, we thank the US DOT, CN, BNSF, Hanson Professional Services, and Union Pacific for their ongoing support. All of us here in RailTech at Illinois are greatly appreciative. Individuals registered for today's seminar are quite numerous, and they include BNSF Railway, Amtrak, Cambridge Systematics, Canadian Pacific, CTA, South Central University, INSCO, FRA, HNTB, Keolis, KTH, Metro North, Montana Rail Link, New York State DOT, Parsons, Patrick, and many others. It's great, as I said earlier, to see such a strong turnout. For those of you that completed the PDH payment, you're going to receive your PDH via email on Monday morning. If you did not complete payment, but you do wish to receive a PDH, please send Emma an email and she'll send you the payment link. Now to introduce today's topic. Today's seminar discusses an important topic that relates to the inspection and management of track assets. FRA-mandated railroad track inspections result in labor cost and occupy a valuable network capacity. These factors, combined with advancements in the field of machine vision, have encouraged transition to a more machine-based alternative from our traditional human vision inspection. Most commercial systems currently available are limited to a pass-fail approach, as opposed to being able to detect subtle changes as track condition evolves. To overcome these limitations, this seminar is going to describe the field deployment and validation of a system that pairs three-dimensional machine vision with artificial intelligence and change detection. The change detection approach uses a deep neural network approach to characterize network conditions between repeat runs before then analyzing the differences. The seminar will discuss the process for image capture and how the DNNs were trained with 3D images captured in the field. Today's speaker, it's exciting to get to introduce a speaker that has partnered with us on research here in RailTech, and today's speaker is Richard Fox-Ivey. Richard has more than 20 years of experience in the transportation infrastructure management field. During this time, he's worked for sensor manufacturers, system integrators, inspection service providers, and asset management software developers. In his current role at Railmetrics, Richard is responsible for the company's activities in the rail industry, working with Railmetrics' algorithm development team to develop inspection solutions for railway owners and operators. Richard is currently managing his third FRA research and development project, which involves the development of AI-based railway asset change detection technology. Please join me in welcoming Richard for his seminar titled Innovations in Track Inspection, the Use of 3D Laser Sensing and AI to Detect Changes in Track Condition. Richard, if you are ready, it's all yours.
Great. Can you hear me, Riley?
Sure can.
Okay, excellent. Well, thanks very much for the introduction, and good afternoon to everyone. And I appreciate you joining me this afternoon. I think without further ado, we'll jump right into it. So as Riley introduced, the mission of this project is to evaluate the potential to use 3D laser triangulation, which is a type of 3D laser scanning, and a deep neural network, which is a type of artificial intelligence, to provide value-added inspection data to existing geometry car inspection systems. This is a live project we started last year in May, and it's going to run until the end of October. And there's two primary objectives. The first objective is to improve network safety through improved reliability and robustness of track inspections. So creating inspection data that is very repeatable and objective. And the second part is to provide value-added inspection data to existing geometry car inspection systems. Geometry cars are traveling around many different networks around the country and indeed around the world and collecting data that we're all well familiar with. But there's a lot of other information that a typical track inspection, a track inspector might want to collect. And so there's an opportunity here to hang more things off of these inspection vehicles and acquire more data in the same pass. And specifically, there's two kind of scenarios in mind here. One is an inspection scenario where there's no prior knowledge of that bit of track, never driven down the track before. What type of information might be captured that would be useful? And the second scenario is a repeat inspection scenario. And this is where the change detection comes into play. So maybe there's a part of the network that's scanned every week or every month. And being able to track how various different parameters are changing about that bit of track every week or every month is something that would be useful. So there's a lot of stuff on this slide. I'm not going to go through all of it because we're actually going to cover many of these topics as we progress in the webinar. But let's summarize it now just so that everyone has an idea of what the project's about. So first phase is data collection at TPCI's high tonnage loop, which involved multiple repeat scans over about a 7-week period while the fast train was operating. The next phase of the project involved training a deep neural network. The next phase after that was processing 3D scans from the HTL using that trained DNN. And then the final phase, which is what we're working on right now, is doing all of the change detection on top of those DNN inspection results. So just a note on DNN. I keep on saying DNN, and we're talking about artificial intelligence, so it's useful to have a bit of background information. So a DNN stands for deep neural network, and the word neural is in there to tip you off that this is a type of technology that operates like a human brain. And when you think of the way a human being thinks about problems or solves problems or investigates something, you apply neurons to it. You have many layers of neurons where you're thinking about all the different aspects of a question that you're trying to answer, a problem you're trying to solve. And deep neural networks are types of artificial intelligence that have a similar kind of structure. They have many layers. They're deep in terms of the number of neurons. And they address problems, or they analyze things in a way that is similar to a human brain. For this project, there are many different types of DNNs, and for this project, we used a convolutional neural network. And CNNs are useful because typically when a artificial intelligence, when a machine looks at an image, instead of seeing the 3 puppies here, the 3 dogs, which we immediately recognize as a human being, it just sees a bunch of numbers. And so if you wanted an artificial intelligence to analyze an image like this, you'd have to do a lot of pre-processing normally with some other kind of artificial intelligence. But with the CNN, it actually looks at the image more like a human being does. And that's more efficient. And it helps CNNs to be more effective at analyzing images than a typical computer would be, or any other kind of artificial intelligence. And when you want to deploy a CNN to do image analysis, what you have to first do is you train it by presenting lots and lots of images of the things that you want it to recognize. So that's what I mentioned a little bit earlier about the phase of training the CNN. So we'll talk a little bit about that later, but just a bit of background information. So let's talk about the field work that was done out at the test track. As I mentioned, we did multiple weeks of scans. So the 7 weeks of scans while the fast train was operating last year, starting on around September the 10th and going all the way to October 23. We did 22 complete loops around the HTL. I should probably put complete in quotation marks because sometimes parts of the HTL were not available. They were doing some kind of maintenance, so they had to shut down part of the loop. But as much as we could, we did complete scans. In each of those weeks, we normally did a couple of scans. That's why we have that large number. We did forwards and backwards direction scans because we wanted to be able to model what kind of results we can get when we collect the network in different directions. We did diverging trips through turnouts. Each one of the passes around the HTL loop generates about 2,000 3D scan files. And each of those files are about 2 meters long in terms of length of track, so about 7 feet long and 3.4 meters wide. And each one of those files contains both intensity data and range data, or maybe put in a different way, 2D image data and 3D scan data. At the very start of the project, Realtech staff did a very detailed ground truth walking inspection, walking survey, and filled out a spreadsheet with about 15 different features related to things like spikes and ties and clips to create kind of an in-person, this is what a rail inspector would have seen if they were out there on the HTL that day. And that's really important because we don't want to just sort of look at, you know, how well can we analyze 3D data, but we also want to have a sense of, like, does it match what the boots on the ground might see? And we won't go through all this, but you can kind of get a sense of the variety of things that that walking survey collected. So information's about the surface of the rail, spikes that were missing or broken, cut ties, ballast levels that were too low, anchors that are missing, damaged. So a pretty comprehensive survey along the length of the HTL. On the 3D data side of things, this is the system that was used for the 3D scanning. So you can see it's a high rail trailer mounted system. So this makes it really flexible. You don't have to permanently install it on a high rail, and you can use different high rails to pull it around as necessary. It's a fully self-contained unit. Everything that you need to do the 3D scanning is in this system. So there are GPS receivers, antennas. There's a wheel encoder or a DMI. You've got all of the computers for data storage, the computers for data analysis, so on and so forth. It captures a 1 by 1 millimeter scan in the X and Y. So imagine a piece of graph paper on the ground, and your squares in your graph paper are 1 by 1 millimeter. And then the vertical resolution is about 1/10 of a millimeter. And last point to mention here is there are IMUs, inertial measurement units, on board that are used for motion correction, which we'll look at in a moment. Just a few more close-up views of what that looks like. So it's one sensor above each rail, and the total scan width of that is 3.4 meters. And you can see the wheel encoder there on the bottom. So once the high rail gear is engaged and the steel wheel is rotating, that's generating pulses and sending a pulse to the system every millimeter of travel down the track so that the system will capture a new scan. And inside the high rail vehicle, remotely logging in through Wi-Fi, you've got a user interface. You can keep track of how fast you're going, GPS coordinates, some real-time results in terms of things like gauge and alignment and cross-level, and event information. So if you're hitting event keys to mark mileposts and whatnot, that's in there. Now, normally the laser light that's projected from this system is not visible. It's beyond the visible spectrum. It's in the near infrared part of the spectrum. And you have two individual scan lines that are being projected. So you're looking at an image from a GoPro with some filters just to be able to capture a picture of what these laser lines look like. So you see there's no missing area in the middle. There's some overlap in the middle. In reality, you never end up seeing individual scans because you get more of a compiled continuous image like this. So here's a 2D intensity image. So this is produced by measuring the intensity of the laser light that's received. And simultaneous with that, the system is capturing a 3D range image. And sometimes people kind of say, well, geez, the industry has a lot of 2D. What would be the value of 3D? So here's an example where if we look at the top two ties in this intensity image, and we look at the tie at the bottom of the intensity image, and if you imagine you were tasked with trying to inspect the condition of these ties, come up with a grading for these ties, it's hard to tell from the 2D image which ties are good and which ones are bad. You know, this one at the bottom is pretty dark, so it might sort of seem like this is the problematic one. And the top two ones, you can't really see that. If we flip to the range data, they actually have large slits that go underneath the right-hand rail. Whereas that tie that was at the bottom that was kind of dark and discolored is actually perfectly fine. So the value add here is you're giving more information to the DNN to analyze. The more information, you know, the artificial intelligence has to do the inspection, the better. But then if you combine these two types of data together, you get, you know, a 3D view like this that you can take a virtual track walk if you want to and pan and zoom around and whatnot. As I mentioned, there are inertial measurement units, IMUs, inside each one of the sensors. So those are tracking the pitch, roll, and heading or yaw of the sensors. And then there's an algorithm that automatically compensates for vehicle motion. So for example, in this crossing, if you weren't compensating for vehicle motion, you'd have a scan like this. But then when you apply that compensation, you get a crossing that looks the way it should. You remove all of that sort of vehicle vibration and the impact on the scans. So one of the things that people, I think, often think about with any kind of sensing technology is how repeatable is it? And that's a very valid question to ask, especially when you're doing change detection, because if the technology is not repeatable, then you've got a lot of built-in change that's just systematic error. So prior to this project, this technology has been field trialed a couple of times by the FRA in prior projects. And the most recent one was with Amtrak on a 9-mile test loop that is just kind of at the border of Delaware and Pennsylvania. And during that project, multiple repeat scans in same and opposite directions were captured along this 9-mile test loop in order to model the repeatability and look at the noise floor for a variety of different measurements, including ballast height, ballast fouling, tie skew, fastener inventory, joint bar bolting, a whole range of different measurements. And the average overall repeatability for all measurements in all directions was about 99%. So very, very repeatable. And some of them were 100% things like joint bar and whatnot. So it's a pretty repeatable type of technology, which is one of the core objectives of the project. Okay, so after these 7 weeks of 3D scans were captured, we had a nice chunk of data to start working with. Now, not all the data is used for DNN training because you need to train with some data and then you need to test with a separate set of data, so you're fairly evaluating the DNN. Okay, so training-wise, we have all this data. Is it good data or bad data? Well, kind of the best of both worlds, best and worst case scenario in a way. So from a positive perspective, there's plenty of change in a short period of time. You know, over those 7 weeks and those 22 3D sets of 3D scans, you have a lot of change in the HTL, which is perfect. That's just what you want. But from a training perspective, the HTL is kind of challenging. You know, when you think of training someone to do something, if it was a person, you want a lot of examples of each thing or condition you want to train them for. So you want to train a person or a small child to identify dogs and pictures. Well, you'd need a lot of pictures of dogs in different situations so that eventually the person, or in this case the DNN, figures out, okay, this variety, these are all dogs, I get it. And if you wanted to separate out different breeds, then you need lots of pictures of different breeds, and so on and so forth. Unfortunately, the HTL is pretty heterogeneous. It's not very homogeneous. It constantly changes along its length. You get these little bursts of wooden ties and spikes, and then a little burst of concrete ties and a type of fastener, a clip, and then it continues to change over its length. There's lots of different types of ties. There's lots of different types of clips. There are lots of different types of sort of install plates when you're talking about the clips themselves, different spike patterns. These are all kind of good things because you want to expose the DNN to a lot of different things, but it is also challenging in that it's hard within the length of the HTL to have enough examples of everything. And you also have strange stuff along the HTL, specialized sensors that are in place that you have to ignore. You have things like ground sheets or tarps covering different sections of track. So there's some strange stuff out there too. I mention all this to say is that one thing we've learned in this project is that training a DNN with data from the HTL is actually harder than training it using regular track. So kind of an interesting situation. Okay, so what do we do when it comes to training? What's involved? Well, the first phase is just to take all those 3D scans, and they were put into the software, and they were automatically analyzed with existing algorithms. To create an initial data set that a Railtech team member could go through and review manually and say, did the DNN do a good job or not do a good job? Now, so I see it got these spikes, but it missed this spike, or it missed that spike, or it missed this fastener. So then the Railtech staff member went through, clicked on the different features that needed to be either added because they weren't detected, maybe it was something entirely new, or the information that was reported by the algorithm was incorrect. And they go through and they manually annotate those images. And they use a series of drop downs to make sure that the data is very consistent. So, you know, you missed a spike, there's just a little drop down to add a missing spike. And as they go through and they do all of that manual rating or review of the automated results, that created an XML file, a list of all of the different features that the DNN needed to be trained on. And so this process, we went through a number of cycles where progressively we had a feedback loop. We would have the manual marking, we would send the XML to the DNN in order to do the additional training. We'd produce another version, do automated review again, have the manual review, and so on and so forth. So each time you go through a training cycle, each time you take a set of images and you put it into the DNN and you go to train with it, that's called an epoch. And normally to train a DNN, you need millions of cycles through those images, millions of epochs. The more the better. Obviously, if you only have 100 or 1,000 epochs, you can only get so far, but the more the better. We trained for two different types of information. One was sort of basic feature identification. So, you know, identify spikes of which there are multiple different kinds, identify clips of which there's multiple different kinds of tie plates, etc. And then also condition states. So, okay, you've identified a tie plate. Can you mark a given tie plate as being defective or okay? You know, defective would be maybe a tie plate that's missing a spike according to pattern analysis, or it's twisted. Or for a clip, okay, you identified a clip, but can you also determine whether it's defective because it's loose or it's damaged, and so on and so forth. So once you do all of the training, you're now ready to start processing images and having the DNN or the CNN label those images. So this is an example of some of the image labeling. So this is a portion of the HTL that has wooden ties with tie plates and dog head kind of standard spikes. You can see the DNN puts a box around the different features and labels it, says, I think it's this, and it also gives a numeric score. So if we kind of look on the bottom left-hand corner here, we can see that it identified a tie plate on the left side of the left rail, and it's pretty confident. It's 99% sure it's confident that this is indeed a tie plate, and the spikes are at 99%, and so on and so forth. And if you look around, it looks like it did a pretty good job here. It looks like it's got everything. It's got all the tie plates. It's got all the spikes. No false negatives in this case. It didn't, you know, pick a piece of ballast and say, hey, that's a spike. Here's another example where you have also some clips, some E-clips. as well as spikes, but these are a different kind of spike. These are screw spikes. And I think, again, the results look pretty good here. Just kind of looking around, you know, there's 4 of these screw spikes on each plate, and that seems to be correct. We have fasteners in all those positions. That seems to be correct. All the tie plates have been detected, so that's kind of a nice result. Here's a trickier case, though, and this kind of goes back to what I was talking about earlier in terms of the HTL being kind of a challenging environment. So this is in a bridge section, and you have kind of a different strange array of fasteners and spikes, and you have other hardware that's sitting here. So, you know, these are the DNN results after training on a lot of parts of the track that wouldn't have looked like this. Now, this small part of the track would have been part of the training set, but you can see the DNN's a little less certain about this. You know, we have a spike over there suspected on the right-hand side, which is the head of a bolt. That's 74%. So it was kind of thinking, yeah, this is a spike, I think, but maybe not quite. And if you look on the right-hand rail, you see some spikes rated at 86%, 82%. So, you know, here's a situation which is a bit more challenging. And really, to do a good job on this part of the track, what you'd really need to do is have many more examples. You need to have much more length. You can't just have a few feet of a bridge. So when you're deploying a DNN on, you know, a large network, that's something to keep in mind. It's going to do really, really well on the long lengths of track that you've got some consistency and you can train well for, but for special areas, it's always going to be challenging to train for that. Here's another part of the HTL. We've got concrete ties and we have some E-clips, and you can see it's doing a nice job there. Even when the clip is, you know, kind of partially buried in ballast, that's one of the things that's quite interesting about a DNN. Just like a human brain, you know, you can look at a fastener and the fact that it's surrounded by ballast doesn't prevent you from identifying it. Here's another example with some fast clips. And again, you can see that many of those fast clips, particularly on the right-hand rail, they're in the gauge side, they're really surrounded by ballast, so not easy to spot. Another example, in this case, you can see the tie that is second from the top is missing a fastener. And the DNN actually in this project was trained in 2 different ways. It was trained to identify when something was present, for example, these fasteners, but it was also trained to detect when something was missing. So to kind of look in a case like this and say, hey, there should be a fast clip here. There isn't a fast clip. In this example, you're just seeing the first case. You're just seeing just detect where those things are present. So then you could handle identifying this particular tie as a second stage by just saying, hey, there should always be at least 4 fasteners per tie. Or you could, as we did as well, train to find the missing fastener. Here's another type of, I guess this is a safe lock type of fastener. You can see it's calling them fastener 2, fastener 2. You could use the actual product name if you wanted to when you're training. In this case, we just used numbers. Another example of more of those fast lock type fasteners and safe lock, sorry, not fast lock, safe lock. And the bottom 2 ties, you can see again, they're missing them. So there isn't a false detection there saying, hey, I see a fastener. No, it's detecting those not present. Here's another one of these kind of unique things that you see at a place like the HTL. We now see some ties where there are, you know, 4 fastener positions on the left part of this bottom tie and just 2 on the right-hand side. And here's yet another more complicated version of that, I guess, in a way, where we can see there's 6 fasteners per tie. So these are some nice results, but I will say that this kind of situation is tough because there's not that many of these at HTL. So you get a sampling of them to train on, but really to do well on this kind of a fastener scenario, you would want to have quite a few examples to train on. here's a case where you see a mixture of different fastener types, and the DNN seems to do quite well in those cases, even if you have a mixture of wood and concrete, and then you have a few flavors of spikes, a few flavors of clips, all in the same area. It can do that kind of thing pretty well. So you've captured the 3D data. We've done all of the training on the DNN. We've now got the DNN to the point where we don't feel it can be trained any further, and it now has the ability to characterize a network, to go out and automatically inspect the network. Now the final stage of the project is change detection. So what's that process look like? Well, take the same length of track, the HTL, and you inspect it 2 times. That can obviously be in forward direction or reverse direction. The DNN analyzes each one of those runs in order to characterize those runs. So it goes through and figures out where all the fasteners are, where all the spikes are, where the ballast is, the conditions related to those features as well. Then the change detection algorithm automatically aligns those 2 runs. And then it reports on the differences between those runs, the changes. So, you know, you could be looking at September 10 versus October 3rd or versus October 23rd, so on and so forth. So one of the most important things to do when it comes to change detection is to make sure you're talking about the same location on the track, obviously. But it's challenging because the inspection vehicle never starts or stops at the same location. You know, if you set up this kind of project and you maybe have a mark on the track and you make sure that you exactly start and stop at that mark, well, that's easy. But in a real world project, real world implementation, you wouldn't do that. Plus, you can't always guarantee that you're going to be going in the same direction when you do your inspections. You know, also, again, in the real world, you can't guarantee that. So you have to figure out a way to make sure you're looking at the same spot. Am I comparing the same position between run A and run B? So the algorithm that was developed here, there are 2 steps to it. It's fully automated. The first step is using GPS. So it uses GPS of the 2 inspection runs to get close to the same position. Now it's a pretty high-end GPS system. It uses dual GPS receivers, dual antennas, and it also uses an inertial system, and so it's like a blended inertial navigation system that uses dead reckoning when it doesn't have great GPS, and when it has great GPS, it focuses more on the GPS part of the solution. But even using something like that, you're probably, I would say, within a foot or so would be really great. If you get 2 runs and you get the position accuracy to within a foot or so, that's pretty good. So it's not quite enough. You know, if you want to compare, let's say, the fasteners on a particular tie between 2 runs, you need to, or you want to compare joint bars, you need to know that you're looking at the exact same position. So the second phase of the matching does 3D shape matching, and the DNN has characterized each of the runs in terms of the 3D content. So, for example, you get close, the DNN suggests, I believe this tie matches this other tie, and then it starts working through to the adjacent tie and the tie after that and other features in the area to say, hey, am I looking at the same spot? And again, because you can have lots of changes, you know, maybe the adjacent tie doesn't match, right? So you need to look at a bunch of different features in order to ensure that you're matching those same features. So in this case, this is actually from Amtrak. So you've got May 2019 to September 2019, an example of the same section of track. On the left in May, you have some really low ballast spots there in purple. And then on the right-hand side in September, you can see that those areas have been filled in. They're no longer highlighted in purple, and those kind of black areas that are really low on the right-hand side are now filled. Another way of looking at change data, or one nice way I think of looking at change data, at least from a high level perspective, is to map the data. Because yes, it's interesting sometimes to know that you have one less bolt on a joint bar, or you have one less fastener somewhere, but I think that on a network-wide basis, what's probably most useful is saying where there are clusters of changes. Where maybe am I seeing ballast coming off the end of ties plus loss or loosening of some clips, plus some kind of damage to the head of the rail, a number of things kind of in close proximity that tells you, hey, something interesting or something dangerous is going on at this portion of the track. So this is just some of the TTCI change data brought into Google My Maps, and you can kind of, colorize those points, and the more intense the color means there's more change going on, and you can bring in sort of multiple variables. I want to look at change in joint gap plus ballast level plus tie skew, for example. So that's kind of an interesting way to look at the data. If we look at a few different examples, first one I'm going to give you is on joint bar bolting. So the top two graphs are left rail bolt change and right rail bolt change. On the y-axis, you have the number of bolts, and on the x-axis is just your location. And then the bottom graph is joint gap, so how many millimeters wide is each gap. So what does this tell me? Well, on the left rail, I see I went from a location that had 0 bolts to 4 bolts. And a little bit later on the right-hand rail, after mile point 1.5, I see I have a location that also went from 0 bolts to 4 bolts. What is that? Well, what does that mean? Well, it actually means they added a joint to the track. So you have September 10 on the left, where you have continuous rail on the left-hand rail, and October 23 on the right-hand side of this slide, you can see you now have a joint bar installed, and there are 4 bolts. You've got 1, 2, 3, 4, and you also have the joint detected, and this little box means there's some localized surface collapse there. So this is just the left rail. The right rail was the same. In this case, there was a joint installed there. So interesting example of change. Here's a different example of change. Here's some ballast level change. So again, between September 10 and October 23rd. So this is the very start of fast operation, the very end. And on the right-hand side on the bottom, this little table, this is computed automatically. These are measurements in terms of the level of ballast in those zones. So what are we looking at here? Well, these are LAS versions of the 3D data. So this is like a LiDAR data format. And the color of the pixels in the image corresponds to the height. Hot colors are high, cool colors are low. What you can see here is off the left side of the ties, you have more ballast in place, holding those ties in place in September than you do in October. We can see that ballast has washed away or moved away. And if you look in the gauge area, you can see there's a little more ballast in place. Well, that's not too exciting or interesting. And the right-hand side, you see there's really effectively no change. But ballast is moving away from the left-hand side of these ties, so that's something that's worth noting. Here's another change example. This is fastener change. So you can see in September there was a stretch of 4 ties in a row that had no fasteners, and you can see come October that stretch now has fasteners in place. So the red symbols mean there's no fastener, and you can actually see they're sitting here beside the track. And then the blue symbols mean that yes, there is indeed a fastener. And then the last maybe couple of examples are related to surface defects. So these are, this is not ultrasonic, it's not eddy current, we're just dealing with surface-based things that are of a reasonable size. September 10, you have relatively good condition rail. October 23rd, you have a little bit of surface damage, about 3/4 worth, 17 square centimeters, but for me, I have to have some kind of physical reference so I know what I'm talking about. Here's another example going the other way around, so there was some kind of a surface defect in September, and by October 23rd, as part of the maintenance that TTCI was doing, you can see that it was removed, and it was about 4 quarters worth over a little length of track. So that brings us to the end of the webinar portion. I'd just like to say thank you to the FRA for their funding of this work and their continued support, as well as to BNSF and CN for their advice and guidance on the project. And of course, Railtech has been a great project partner, and we're looking forward to finishing this project strong in the next couple of weeks and sharing the results with the industry once they're published.
Richard, thanks so much for the presentation. While we wait for some questions to flow in, I'll kick it off with a question, and this gets back to your slide with the epochs when you talk about kind of the more the merrier, and if we have 1 million, it's better than 1,000 as we're training the DNN. Is there a risk of overfitting the training data set, or am I confusing this with other types of modeling, and there's some unique way in which we train these that's not a concern?
That's a good question, Riley. I think that yes and no. I think that when it comes to training, you have to be very careful. You have to be very deliberate about the training work that you do, and very precise. So one of the things that we learned during this project, there were a couple of fasteners that were visually very similar, and inadvertently in one of the first training runs, they ended up being identified as the same kind of fastener. And even though they really were slightly different. So for the DNN was kind of, at least I in my head imagine it saying, well, yeah, it's kind of a slightly different size and shape, but it's the same thing. Okay. When you do that, when you provide a lot of variability within a particular thing that you want to classify on, or that you want the DNN to identify, then the DNN gets a bit sloppy. The DNN's not quite sure. It's a little more sort of, well, this is close enough. I guess this must be one of those things. So I think what you really need to do is be pretty careful when you do the training. You need to think about the type of information that you want to get out of the system. And sometimes you need to break up the training activities into smaller, more manageable chunks in order to get the results that you want. And if you don't do that, then yeah, you can end up getting sort of a higher level of, let's say, false positives, because the DNN's just not quite sure where the boundaries between this feature and this other nuanced feature lie.
That's a good answer, Richard. Thank you. A couple of questions from the audience. The first one is, what is the maximum speed for testing that allows you to still maintain and generate accurate results?
Good question. So this system is triggered on a distance basis, as I said before. So high rail speeds, up to like about 45 miles an hour, 60 kilometers per hour, will allow you to use full resolution 1 millimeter by 1 millimeter. If you want to go faster than a high rail, let's say you want to double that, you want to get to, let's say, 90 miles an hour or 120 kilometers per hour, then you need to have the collection interval. So instead of capturing a scan every millimeter, you simply capture a scan every 2 millimeters, which frankly is still very high resolution if you pull out your ruler and you look at what a millimeter is. And so far what we've seen is that on a 2 millimeter interval, really you get the same measurement results when it comes to things like change detection or sort of defect detection. But you sacrifice a little bit on maybe how crisp the images look, or how nice the images look. And even 3 millimeter interval still produces pretty good measurements. It depends on I would say what you want to inspect. If you're looking at the head of the rail, then I think you probably want to use a 1 millimeter interval. And if you say, I don't really care about the head of the rail, I'm more focused on the ties and the fasteners and the ballast, then I think 2 or 3 millimeter would be fine.
Thanks, Richard. Another question is, I guess if you go back to the slide where you're talking about change detection of ballast height, the question is, what does the number shown represent? Is it change in volume, height, and how is it defined?
Yeah, and good question. So there's a number of different measurements the system makes with regards to ballast. This particular example is a running average height in each of the zones, and the running average is summarized on a, let me just think about this. I believe it's about a 10-foot summary interval. So the left ballast zone, left rail ballast change would be everything on the field side to a certain distance from the end of the tie. And you kind of imagine, you know, getting a 3D scan of that surface and then measuring the air gap between an artificial line at the top of the 3D scan drawn from the top of the rail down to the surface of the ballast. And the same thing done in the gauge zone, and the same thing done on the right rail. So the algorithm is coming up with what is the average height over a particular distance for that particular portion of the track.
Thanks, Richard. Now a question about preparing the data for the training data set. How is the 3D laser scanning data used? Do you manually label the 3D data as well?
So I may use this image just as an example. So this is the 3D data. Let me explain a little bit more. So the shade of the pixels here corresponds to the height of the feature. So things that are light are high off the ground, and things that are dark are lower onto the ground. And you have to kind of imagine these range images as like if you were standing over top of something pyramid in shape, and you took a slice of the pyramid. That's what these images are. They're kind of a slice of the 3D data. And if I just go back to the slide where we were talking about training data. So you can see in this interface, we have 2D images here. This is a 2D image. These are 3D images on the bottom. So the 3D image is interacted with in the exact same way as the 2D images. So if the rail tech team member noticed that a fastener was missing, they can just draw a box around the fastener, and they can click a little button to flip between the 2D and the 3D view while they're working with that to create the training data set. And some things for sure, it's easier to see them in the 3D data. I mean, you could play around with the 2D image, the intensity and whatnot, but 3D is just like immediately you go, oh, the spike is either there or it isn't.
Very good. Thanks, Richard. Question regarding the architecture of the algorithm. What type of CNN architecture did you use?
Super good question, beyond my knowledge. I would be happy to answer that question offline afterwards. I would have to just double check with the AI guys.
Sounds good. And John Hart, thanks for the question. We'll follow up offline. Do you have a data set that's available to the public to experiment with different vision networks?
Not really, not as of yet. That's not something that we've done. Maybe it's something that we could do in the future, but not thus far. Okay.
Thank you, Richard. And last question is showing up in the list as of now. So if anybody else has questions, please type them in. In your presentation, you focused on non-specialty track work. Can this technology also be used to look for change detection in special track work, grade crossings, or other locations like that?
definitely. What I would say about that is that the trick is having enough data for those portions of the track. So as we saw in some of the examples, things like bridge areas or even things like crossings, I mean, those are much less frequent portions of the track. So in order to train the DNN to do a good job of characterizing them, you need to, drive a lot of switches, drive a lot of crossings, drive a lot of bridges so that you have enough data to be able to accurately characterize them. So yeah, I see no reason why it couldn't be, but thus far and on this project, there's just not much data. There's not many examples of those types of features to really develop a robust DNN analysis.
Understood. Follow-up question from one of our earlier participants. If testing during heavy rain, is there a distortion to the results? It's a good question.
Yeah, really good question. I mean, the simple answer is anytime you mix lasers and water, you're definitely going to get distortion. But a more reasonable, detailed answer to that is you don't want standing water. Standing water is going to be a problem. Slick, wet surfaces will present some noise in the data, and sort of damp or drying out surfaces will present, a very minimal amount of noise. So I would say that, this technology is, and really any laser technology, you really want to use it when the conditions are dry towards, having dried out after some kind of a rainfall. But in this particular project, for example, on September the 10th, we had some really wet conditions just prior to showing up on site, and still able to get good scans. So I think the short answer is you really want to make sure there isn't standing water and the surfaces are not slick wet. And if you do that, then you'll probably get good results.
Very good. We've got now 4 more questions that have come in, so maybe we'll go through those before we wrap it up for today. What about the use of this technology on metro lines, tramways, etc.? This is similar to the special track work response, I'm guessing.
Yeah, actually, we do have. There's a company in the Netherlands, Structon, who's using this technology for tramways, trolleyways, for groove rail and embedded track. And yeah, so they're actually collecting data pretty much exclusively on that kind of network. They're not really operating on normal tracks. So they're accumulating a lot of data on those kinds of conditions, which allows the DNN to be trained for those kinds of conditions specifically. So I don't have too many more details on that, but I can tell you that much.
No, that's helpful. How is the feature recognition critical for the alignment for change detection?
Sorry, how is it critical?
How is it critical? I assume for alignment of consecutive runs that you were doing change detection of. That's what I'm going to read into it. I'm assuming that's what's being asked.
I think the answer kind of depends. I mean, if you want to do sort of tie by tie comparisons, then the feature detection is important, and that's why we do it. But if you were looking at more of a high level statistic where you say, let's analyze something over a mile basis and, what kind of changes are there over a mile, then I think you could sort of say, well, the feature detection is maybe less critical because, a few feet here, a few feet there, aren't going to impact that kind of analysis because you're looking at things on such a long basis, right? So yeah, I think it maybe depends a little bit on the nature of the changes, how big they are, and over what interval you're considering change.
Very good. And we've made it quite a while without this type of question, and I'm kind of surprised. How large are these data sets that you're acquiring? What should the industry be prepared for?
Yeah, good question. So at the highest resolution, so at that 1 by 1 millimeter high rail speed, you could generate about 6 gigabytes per mile. if you said, well, gosh, that's too much, I can't handle that. If you cut it in half to a 2 millimeter scan interval, now all of a sudden you're 3 gigabytes. And again, you can, think again, if you want to keep cutting it and cutting and cutting, you can get the space down. But I mean, just frame of reference. I mean, the data storage on board this inspection trailer, I think, was about 700 or 800 miles worth of data. Nothing special. I mean, it's just SSD hard drives that you could get from Best Buy or any regular electronic retailer. So it used to be that data storage was kind of a big thing, but honestly, I think it's not as much anymore. If you do think about multiple years of data storage, then maybe you start to think about, well, do I save the 3D data files, or do I just save the results of the analysis? How long do I save it? I think those are some of the questions maybe you start looking at when you think about a big railway network and wanting to collect data over multiple years and doing, analysis over multiple years. Then maybe you start thinking about, okay, what are the implications of this?
Thanks, Richard. We got a few more, and then I will cut it off after the questions, and then if we get more questions, we'll follow up offline. But do you see any difference running clockwise versus counterclockwise around the loop at TTC?
No, like in terms of, sorry, I'll just put it on the contact page so everyone has those. In terms of the change detection results or repeatability, not really. I mean, that's the whole point of doing the run-to-run alignment. Everything is motion corrected. Everything's geo-referenced to a pretty high level of accuracy. So we haven't really seen much in that regard. I'm just trying to think whether there's something that, I mean, you have to keep track of left rail is no longer left rail when you do your change comparisons. Left rail is now right rail and vice versa. But as far as the actual measurements that come out of the system or detecting the changes, it doesn't seem to have an impact.
Very good, thank you. How about, how does the system cope with heat expansion of the track and its components?
Yeah, that's a good question. That's not something that's addressed really by the system. So as an example, which I think would be illustrative here, some of the prior testing work that we did with Amtrak, we looked at things like joint gap, and our testing periods we were looking at sort of months in between the different data sets, and you could absolutely see joints expanding and contracting. And when we went back and we looked at the ambient temperature during those times, which I understand is not real temperature, but it's a little bit indicative, we could see very logical sort of expansion and contraction patterns between environmental conditions where it would have been cool and environmental conditions where it would have been, significantly warmer, and seeing those, joint gaps going from, let's say, 15 millimeters to now being 8 millimeters as the track expanded. So we definitely do see the impact of that in the data, but it's not something that the system tries to compensate for, not as of yet anyhow.
That's a good response, thanks. A good question here regarding back to your slides that related to rail surface defect detection. Does it allow for automatic measurement of the change in size, or just note that there is a change that's occurred?
Good question. So the system the system does automatically 3D profile the rails, and it automatically measures the height difference or the distance between the foot of the rail and the head of the rail. So we know what the height of the rail is, which would be a way to work back towards the particular weight of the rail, I suppose. But that's not something we've necessarily tried to automatically do. The system will automatically match an in-service rail to a 3D profile, and it does 3D shape matching to match those together. So if you had a network, as an example, that had 6 different rail profiles in use, if you have a sort of as manufactured rail profile for each of those 6 rails, you can send that into the software, and the software will look at a scan of an in-service rail and figure out which one of those rail profiles most closely matches it, and then it'll measure the top of rail wear and the side of rail wear based on the most closely matching 3D profile to what's in use.
Good deal. And very last question, Richard. Once this system is used in revenue service, what would you anticipate the frequency of use to be, and how the railroads would adopt it?
Well, I think what we would really like to see is, I think there's 2 answers to this question. I think there's an opportunity to augment existing manual, human-driven high rail type inspections that are being done on kind of a weekly basis on many tracks around the country and around the world. So I think that there are those kinds of pass-fail, do I meet the maintenance threshold, do I meet the safety threshold, those types of inspections that I think this technology is well suited for. It can fit on a high rail, so you don't have to have a special measurement train. So I think there's that potential. I think on a change detection basis, where you're more likely to have this type of technology, installed on maybe an autonomous box car or on some kind of a rail-bound vehicle, then I think maybe every week seems to be might be extreme. Would depend on the part of the track, but I think at least on a monthly basis on a good portion of the network would be logical. And then maybe there are some portions of the network that are just so critical, or that you're already running an autonomous vehicle on already, you might as well bring this technology on board along for the ride, right? Because at least from my perspective, the big cost of doing rail inspection is getting access to the track and getting out there. So if you already have a vehicle that's rolling around on the track, like your geometry car, why not maximize the use of that time on the track by collecting as many things as you can simultaneously?
Thanks, Richard, and thanks for being willing to present today. This was a great presentation, very informative, good questions and answers, and we in Railtech appreciate you being willing to give up a portion of your afternoon to present to us.
My pleasure. I appreciate the opportunity to talk to everyone.
Thanks, Richard, and to everybody that is still connected. We don't presently have our next HAY seminar scheduled, so please stay tuned to the email distribution list that we send out information to. So we'll likely be picking this up again in a couple of weeks, and we look forward to having you join us again. And have a great rest of your Friday and a great weekend. Take care, everyone.